We're now going to take a look at the principles of power transfer systems and what they can do for us. So if we take a look at two gears, now they don't have to have teeth on them. We could have two wheels. Now, if both wheels are the same size, our input and our output speed is going to be identical, and our input speed and output, our input torque and output torque will be identical. So the only thing that when we have two gears or two wheels running together, if they're both the same size, the only thing we get is a change in direction. Now, again, if our input torque is 10 foot-pounds, then we have 1,000 RPM output from that first gear, from the input gear. Our output torque is going to be 10 foot-pounds, and our RPM is going to be 1,000 RPM. So our gear ratios are always going to be something to 1. So it could be 10 to 1, 100 to 1, 4.1, 1 to 1, but it'll always be something to 1. It can also be 0.5 to 1, which would be an overdrive gear. So let's take a look at a few gear sets. So for instance, if we take a look at a reduction gear, so if our input gear has 12 teeth and we're turning it at 1,000 RPM, our output speed is going to be half of the input speed. So it's going to be 2 to 1. Now with that, let's just say that we had 1,000 foot-pounds of torque on our input. Because the gear ratio will also determine what our torque ratio is. So again, when we get a decrease in speed, we get an increase in torque. So our torque now will be 2,000 foot-pounds of output torque. Okay, so and again, like I said, we don't need to have teeth on these to be able to calculate it. So if I told you we had a wheel that was 1 foot in diameter and one that was 2 feet in diameter, again, our gear ratio is going to be 2 to 1. Now, what happens when our input gear is twice as big as our output gear? So again, we're always going to do driven over drive. Okay, so drive is our input gear, driven is our output gear. So if we take driven over drive, okay, so 12 is our output over 24. So what we're going to get is 0.5 to 1. So we get a huge increase in speed, basically twice the amount. But what happens with the torque? Well, again, if we look back at how that plays out, our torque will be half of what our input torque is. And this is where we get an overdrive in a transmission. Now, the other thing that we see is an idler gear. And when you were doing engines, you've probably seen an idler gear on the front of the engine. The purpose of an idler gear is just to change direction. So for instance, when we get into manual transmissions, you'll see an idler gear for reverse. And that's just to allow us to get reverse out of that transmission. Idler gears do not count in our gear ratios. So we would count the gear teeth on this and the gear teeth on this. And let's just assume that there's 24 here and 24 here. Our gear ratio would be 1 to 1. Our torque would be, let's say 1,000 input would be 1,000 output. Our RPMs would not change. All it does is change the direction of our output gear. Now, some of the gear nomenclature that you need to understand. So it's the outside circle, the pitch circle, and the root. So the outside circle is a circle that runs around the top of the teeth. The root circle is at the bottom between the teeth, and the important one is the pitch circle. Now, the pitch circle is where all of the contact between the two teeth should take place. It's the strongest part of the tooth because as we start to move over from the pitch circle to the outside circle, as we start to climb this teeth, we put more load on this tooth more of a chance of it breaking. So it's our pitch circle that's the important one for load. Now, when we're taking a look at the pitch circle, it's the distance between two adjacent teeth. Now, it can be from the center of the tooth, or it can be from one side of the tooth to the other side of the tooth. Okay, so diametrical pitch is the number of teeth per inch on this pitch circle. And to you as mechanics, does it matter? Not really, because when we're going to be replacing gears, we're going to match that gear up with the right part number. But it is important to understand what diametrical pitch is. So let's just say that we have a diametrical pitch of 4. So that would be 4 teeth. Now, the gear that this has to mesh with has to have the same diametrical pitch. So let's take a look at a few other pictures of how this is set up. So again, here's our pitch circle. Pitch circle is a circle around the center of the tooth. Okay, and it's in inches. So let's just say that that this had a diametrical pitch of 4. So that would be 1, 2, 3, 4, and that distance from the center of there to the center of there would be 1 inch. Now we can increase that this gear size by 10 times, which let's just say then we would have, I don't know, 40 teeth around there. The diametrical pitch will still have to be 4. Otherwise, the teeth will just not mesh. So again, when we take a look at a pitch circle, here we have 2 gears of different sizes, but our diametrical pitch will be identical to both. Now, the pitch diameter is from the pitch circle of one side to the pitch circle of the other side. And again, we've talked about diametrical pitch. So even though this gear has less teeth than this gear, the number of teeth around the pitch diameter or pitch circle is identical. Now, diametrical pitch, again, there's a formula for that. So it's the number of teeth divided by the pitch diameter. Now, there's also metric teeth, gear teeth, and they are determined through what's called a module. Now, there's modules 1, and if you take a look at these are printed on 3D printer, but this tells you these ones here go all the way up to module 9. And then on this one here, they go down as low as module 0.5. So it's the same thing as diametrical pitch, it's just in metric. So off of a gear drawing, what you'll see is the number of teeth is 20, the pitch diameter is 5, diametrical pitch is 4, and the pressure angle is 20. Now, pressure angle is something we haven't talked about, but pressure angle is the angle that's built into the curve of these teeth. Now, what we see is 2 different pressure angles. The most common now is a 20-degree pressure angle, but you might also see a 14-degree pressure angle. And what I've done is I've printed out 2 different ones. And this has a pressure angle of 14.5 degrees. Now, these teeth both run nice and smooth. This has a pressure angle of 20 degrees. And again, these run nice and smooth. But if you mix up a pressure angle of 14.5 and 20, they don't run smooth. And what you're going to get is you're going to get some unusual noises and extreme wear out of that gear. And it probably wouldn't be long before it's failed. So when we're changing gears in a transmission, it's really important that we match up the numbers. So if we take a look at the smaller gear, we see that the diameter is 2.5. The pressure angle is still 4, or sorry, the pressure angle is 20, and our pitch diameter is 4, the same as it is up here. Now, when they're making gears, there's a formula that they use to make up a gear blank. And again, this isn't important for you guys because unless you're going to be machining gears, it really doesn't matter. But how they do it is they'll take the diameter, so the number of teeth you need plus 2, and they divide that by the diametrical pitch. So if we were making a gear with 30 teeth, so it would be 32 divided by 12, which is 2.66. So this diameter from the tip to the tip would be 2.66 inches, and then they go in and they cut the gears. Okay, pressure angle. Again, I don't know if you can see that the curve on these and the curve on these are a little different. You see how wide this is compared to this. Now, for spur gears only, and again, if you want to figure out any one of these, they do have charts. And like I say, for you guys, it's really not that important that you understand that, how gears are made, but how we figure them out. Now, again, I've talked about diametrical pitch and how it must be the same. Now, you can buy a set of these. These are a set of gear blanks. So if we want to know what a set of gears is, we can take the gear and we can run this on here until it matches. Now these are metric gears, but if we take and we can find out which one it is. So by putting it on here, we can rotate it around till it runs true. Now even though it's a metric gear set, it's 26. So on the metric scale, we would take this here and run it on here, and it's a module 1. Now, whoops. So a couple of things that we have to be aware of when we're running gears together is we need a clearance between the tip of one tooth and the root of a second tooth. And that is to retain some oil and also to give us a little bit of clearance in there so that we're not pushing those two teeth together. Because what happens then is we generate a large amount of heat and we start getting excessive wear. The other one we need is backlash. Now, for instance, in a manual transmission, backlash isn't adjustable. It's built into the gears when they build the gears. But when we get into a differential, that's where we can go in and we can adjust the backlash by making some adjustments. So we have clearance and we have backlash, and those are the two things that we have to worry about and make sure that it's not excessive, but again, that it's not too little, because if it's too little, we're going to generate heat. The first thing that we ever find out that we're going to have a failure of any component, whether it's engine, transmission, differential, is if we start getting an increase in the temperature. And that's what we should be paying attention to. So if an operator comes in and says that my rear diff is starting to overheat or my transmission, it's something that we should take a look at. It might just be a temperature sender, but we want to catch this before we have a major failure. It's a lot cheaper to pull it apart and replace it before we have a major failure than it is after a major failure. Excuse me. So now let's take a look at what's called compound gear ratios. Now, what is a compound gear ratio set? Well, when we have one set of gears that runs into another set of gears that runs into another set of gears, and we'll see this in a manual transmission where our input gear runs against a countershaft gear. That countershaft gear runs another further down, and that will go into our main set and our main shaft. So those are compound gear ratios, and we have to be able to figure out and calculate how our compound gear ratios are set up. So this is a compound gear. So if this is our input This bigger gear will be our output, and it'll run against another set of gears. So let's just take a quick look at how compound gear sets are set up. These are compound gear sets, and so are these. So our input, output, this shaft is splined to this gear here, so this would be input and that would be output. So if you remember how to calculate compound or gear ratios, it's driven over drive or output over input. We do the same with this. So it would be output divided by input, output divided by input, then we multiply the two of them together. In this one here, this is our input, this is our output. So it would be output over input divided by, or multiplied by output over input. So let's take a look at how this is set up. So here we have an input of 12 teeth. We have an output of 60. So again, driven over drive or output over input. So it would be 60 divided by 12, which would give us 5. We have the same here because this is our input and this is our output. We have the same gear count, 60 over 12. That would be 5. So it would be 5 times 5. So it would be a gear ratio of 25 to 1. Okay? Now, with that gear ratio of 25 to 1, let's just say I had 100 foot-pounds of torque on my input gear. What would I have on my output gear? So again, what we lose in speed, we gain in torque. So our torque would increase by 25 times. Now, here's another compound gear ratio set where N1 is 15 teeth, N2 is 30, N3 is 15 teeth, N4 is 45, N4 is 45 teeth, N5 is 15 teeth, and our output N6 would be 45 teeth. So we're going to go output over input, output over input. So calculating all of these through, what are we going to get? Okay, so we're going to get 30 over 15, which is 2 to 1. We're going to get 45 over 15, which is 3 to 1. We're going to get 45 over 15, which is 3 to 1. And if we multiply those all together, we get 270 over 15, or 18 to 1. Now, for you guys to figure out what is the input of N1 to get output of N6. If the input of N1 is 1,000 RPM, what is the RPM output of N6? So using these gear teeth calculations, so you can pause the video and figure that out. Okay, so if you figured it out, we had a gear ratio of 48 to 1. So what we would do is we'd take 1,000 RPM, divide by 48. So our output RPM would be 20.83. So going through the gear calculations again, we see that we have 45 teeth over 15. And then here we have 60 teeth over 15. And here we have 60 teeth over 15. Now we get all sorts of different gear combinations to do different things. We can increase these, we can decrease these. This is why we're able to move large amounts by just using a gear ratio. And again, you take a look at, for instance, a highway truck, a B-train that's fully loaded with lumber, and we put it in low gear, low range, and we get a tremendous amount of torque. But as we start to increase the speed, we want to shift our gears because we've got that load in motion, and it's easier to keep it in motion. So this is a gearbox that somebody made, um, and it has 12 to 60 reductions. So this produces an overall reduction of 244,140,625, a quarter of a billion to one. That means that if someone would spin this input 244 million times, you'd end up with one output. So spinning that input once per second would take approximately 7 years and 9 months before the output would spin once. Imagine the torque on that though. Okay, now let's take a look at different gear sets. So different gear sets. So if we have straight cut gears, okay, we talked about straight cut gears before, also called spur gears. Now with the spur gear, what do we get? Well, we get some radial forces. In other words, these two gears are trying to push away from each other. Now with spur gears, we can use a straight roller bearing. So all we're going to get is radial forces, no axial forces. Now when we take a look at helical gears, now when helical gears, because they're cut on an angle, the two gears are pushing apart, but they also impart some axial loads on those shafts, because as they're pushing apart, the two gears want to slide, so those axial loads are pushed either in one direction or the other. Anytime that we have helical cut gears, because of the axial loads, we have to use a different type of a bearing. Now, if you remember from when we were discussing bearings, okay, so we can have a straight roller bearing, and if we go back and take a look at this here, we have straight roller bearings here because all we have are radial loads forcing each other apart. But when we start having axial loads in here that are pushing one way or another way, what we'll use tapered roller bearings. Now, anytime that we have this type of a shaft, we have to shim these bearing cases. Because again, if you remember back just a little while ago, we were talking about our clearance and our backlash. Now, if those bearings aren't set properly, that bearing can move, and under load it's going to push further apart, which is going to increase that clearance and move our contact point further out on the tip of the tooth. So instead of having a tooth that's in nice contact, as it starts to move out, it's putting more load on the end of the teeth. Hence, we're going to end up with a failure. That's why the first thing that's going to show up is heat. If we start getting an increase in heat, it could be because we have a bearing failure. And again, the easiest way to check for that is to pull the magnets. Okay, so straight cut gear, helical cut gear. Now, we also said in a helical cut, or in a straight cut gear, we only have the contact between this gear and the gear that it mates with. But in a helical cut gear, we have up to 2, maybe 3 teeth that are in contact at any given time. So now it places less load on each one of these teeth than it does on these. So inside a transmission, we have helical cut gears. So this would be our counter shaft, and this would be our main shaft with our sliding gears. So the sliding collar is going to engage in this gear to drive this gear. The sliding collar is splined to the main shaft, so as the main shaft is turning, the sliding collar will turn with it. When we start to get into differentials, so we'll have a crown and pinion. Again, these can be helical cut gears. We're going to get more into how these are set up when we go into differentials. So our toe and our heel, and how to set these up to get the correct pattern, where that pattern should be, and making sure that we have the correct amount of backlash in them. So helical cut gears, again, We could use thrust washers in there, and you'll see that if you remember back to when you were rebuilding engines on your camshaft. If your front gear train had helical cut gears, they would put a thrust washer in there to take up some of those axial loads. Herringbone. Now again, because these go both ways, they counteract each other out. So we got no axial loads in these. We just get the radial loads that want to push the two gears apart. Rack and pinion gears. So again, rack and pinion steering is where we'll see this. Now we get into beveled gears. Again, what it does is changes the direction. Now it doesn't have to be 90. It all depends on how they set the bevels up. When we take a look at the crown gear, crown and pinion gear. So if this is our input pinion, so this comes from the drive shaft, there'll be a yoke here. This is what's called a center mount. So we're going to take a look at the three different types quickly, but we're not going to go into how the patterns are set up. So we've got a center mount or a straddle mount, a hypoid gear set, which sits lower than the center, and we got an amboid gear set, and the pinion sits higher than the center. Now, if you take a look at the three of these, you'll notice something a little different. This one here will have a pocket bearing on the end, because what happens is as we put the torque in here, it wants to push away from the crown gear. So what we do is we put a pocket bearing on the end of this, and it prevents the pinion from moving out of center. So now our contact on our gear teeth stay where they're supposed to. Again, we don't want it out on the end, we want it right in the middle. So that pocket bearing does that. When we take a look at hypoid gear set, which is lower than the center, it has the same setup because of that pushing apart. But when we take a look at an amboid gear set, it doesn't need the pocket bearing, because as it turns, it actually rides on the concave side, not the convex side. So it wants to pull it in. So we don't need a pocket bearing on this one. So crown and pinion gear sets, some of them may have to be timed, and there's an easy way to take a look at whether or not they do need to be timed. So when we do get a new gear set for a crown and pinion, if they need to be timed, there will be a white timing mark on them. So a gear ratio for ones that need to be timed, for instance, if we go to this one here will turn one revolution there, one revolution there, one revolution there. So this would be a 4-to-1 gear ratio. Anything that's an even number with no decimal points needs to be timed. Now, when we get into what's called a partial hunting gear set, they may need to be timed or they may not, so you'll have to look up in the manufacturer. And then the third type is a hunting gear set. Now, these don't need to be timed because they're mismatched. So hunting gear sets will have an odd number gear ratio, 4.11 to 1, 3.89 to 1. So anything that has 2 decimal points after will be a hunting gear set. Hunting gear sets are better because we don't get the same contact every revolution. It may take 20, 30 revolutions before this tooth comes back in contact with this one. So we get more even wear of this type of a gear set. So here's how do we determine. Non-hunting is 2-to-1, 3-to-1, 4-to-1. Most likely needs to be timed. Partial hunting gear set would be 2.5 to 1, 3.5 to 1, 4.5 to 1. Possibly it might need to be timed. And then we get a hunting gear set, which is 2.89 to 1, 3.27 to 1, 4.11 to 1. And again, these do not need to be timed. The next thing we want to take a look at is planetary gear sets. So planetary gear sets are gear sets that we're going to see in automatic transmissions, but we'll also see planetary gear sets in final drives for the output. And again, they're on there to help us to increase the amount of output torque that we require. So what we have is we have an internal gear, also called the ring gear. We have a planet carrier. Now, planet carriers can be 3, 4, 5. We can have 10 of them. And all they're there to do is to divide the torque. So if this is our input as our sun gear, we have 3 teeth dividing that torque. Now, let's just say that our torque is 999 foot-pounds. Each one of these gear sets is going to take a third of that, so 333 foot-pounds. Now, if we had 4, we would divide that by 4, so it would be 249. So that's why you'll see planetary gear sets with different amount of planet gears. Now, planetary gear sets can also be helical cut gears, where at any given time we're going to have more than one tooth in contact. It just makes for a stronger gear. Now, planetary gear sets can be stacked so that we can increase the amount of torque. So every time we add a set, we can multiply the amount of gearing in there depending on how our gears are set up, and we're going to take a look at that a little bit later. This is a double planetary gear set. So our input gear, our sun gear, runs this planetary gear that runs against this other planetary gear set, which runs against our internal gear, our output. And this member here might be held. So if we just take a look at a planetary gear set with 2 gears, okay, so we have our internal gear or our ring gear, our sun gear or our pinion gear. Now, we don't usually do gear calculations. The formula is quite long. If you really want to know how to do it, I'll go through it, but it's not important. What's important is how these work together. So, for instance, if we have our sun gear as our input here, this is turning in one direction, it's going to turn this in the opposite direction. Now, if this internal gear is held, what's going to happen? So as this starts to turn, it's going to walk this gear around this way. So how do we figure that out? Well, there's a sheet that I'm going to hand out that will help you with that, and we'll go through it. This planet carrier has 4 teeth, so again, it's to help divide that load between 4 pinion gears. Now, here's how this is one that, so if you take the sun gear plus the ring gear, and then you divide it by the sun gear. So you take the sun gear plus the ring gear, and divide it by the sun gear. Planet carriers, because they're idlers, don't count in our gear ratio. Okay, so let's just take a quick look at how we determine what this is. So if we draw 3 dots, so our internal gear, which is our outside one, our planet carrier, and when you draw your dots, make sure your planet carrier is close to your internal gear, and then at the very bottom is our sun gear. So if the sun gear is rotating this way, this planet carrier is going to rotate this way if this internal gear is held. So how do we figure this out? First thing we want to do is we want to find out which member is held. Then what we do is we take it and mark an X on our internal gear. Then we draw a line down. Okay, so from the held member, because it doesn't move, we draw a line down. Then we draw some dotted lines across from these two. Then what we need to know is what is our input gear. So in this case here, our sun gear is our input. So our arrow would go from our sun gear to our carrier, because that is our output. We draw an arrow that way. Now what we do is we do a calculation. So let's just say that on our sun gear here is 5 inches across, and this is 2 inches across. Okay, so if we go 5 to 2, which would be, let's just say that's our gear ratio, for every 5 times this sun gear turns, we only get 2 of our planet carrier turning, which would be a gear reduction. So with the gear reduction, what happens to our speed? Well, our speed goes down, but our torque goes up. So let's take a look at another one. Let's just say that now our planet carrier is our input and our sun gear is our output. Well, if we use the same numbers, now we have 2 to 5. So for every 2 times this turns, our sun gear will turn 5 times. So now what do we get? Well, we get an overdrive gear. But what happens to our torque is our torque is going to be less. Now we go through all of these and how they all work. So again, if our sun gear is held, we put an X on our sun gear, draw a line up, and it doesn't matter which side you draw the line up. Then we need to know what our input is. So our input is our internal gear. So we draw our arrow from our internal gear. Oops. From our internal gear down to our carrier. And again, we just guesstimate. So let's just say this is 5 and this is 4. So it'll be 5 to 4. So every time this thing turns 5 times, this turns 4. So again, what happens is we have a slower rotation, but we have an increase in torque. If we go the other way, again, our sun gear is held, but now our carrier is our input and our internal gear is our output. So if we have 4 to 5, our output will be faster and we'll have less torque. The one difference that we get is we can get reverse out of a planetary gear set, but only when the carrier is held. So anytime this carrier is stationary, we draw our line, but as you see, the line intersects and goes on both sides. With that, it indicates reverse. So here, our carrier is held. We draw our line. Now we know that our sun gear is our input. So we put our arrow from our input, from our sun gear to our internal gear. And again, we use our numbers. Let's go 5 to 2. So with a 5 to 2, every time the sun gear turns 5 times, this is going to turn 2 times, but it's going to turn in the reverse direction, and we will have more torque and less speed. If we go the opposite way, where our internal gear is our input, our carrier is still held, but now our sun gear is our output. Now we go 2 to 5. So what happens then is if this is our input, it spins 2 times. Our sun gear is going to spin 5 times, but because this line intersects and crosses over, we get reverse. Now, when we take a look at, again, planetary gear sets, we'll see those as outboard planetaries. We may also see them as inboard planetaries. Outboard planetaries are much easier to service than inboard planetaries. So how would we tell? Well, if we take a look at a cover, you'll see that the cover has as many pinion gears on there. And again, on most cases, our internal gear is held. Sun gear is our input, and it's our planet carrier that drives around. Now this is a outboard planetary final drive, which is a double planetary reduction gear. So one planetary runs into another planetary to give us a double reduction. When we take a look at, for instance, an older dozer, so from our transmission, we go into our pinion gear, which goes into a bevel gear or a crown gear. That drives onto a spur pinion that drives a bull gear that goes into a planetary gear set. So we have three reductions here. We have one here, we have our second one here, and our third one here. If we take a look at, for instance, a grader final drive, again, from our transmission, from our crown and pinion, is going to drive this sun gear, which drives this planetary gear set. Now again, our internal gear is held here all the way around, and this part here is splined to this shaft here, which goes out to our drive sprockets. And again, because the way it's set up, we have tapered roller bearings so we can adjust them for the amount of movement back and forth. And by taking a look at the cover on this dozer, we can tell that it has three carrier pinions. Okay, so in wrapping up, so power flow of vehicles dependent on many factors. Application. What are we going to be using the vehicle for? Is it going to be on highway and off highway? Where in a case like that, we're going to have to find a happy medium because we don't want to be doing 1800 RPM and only 50 kilometers an hour. We have lots of torque, but on the highway, it doesn't do us any good. So we can change that again. So what type of transmission? Is it automatic standard? What is the gear ratio set up in the transmission? Again, what was the truck spec'd out for? Type of driveline does it have? Type of rear differential? Type of final drive? Does it have outboard planetaries on it? All of these factors have to be taken into account when looking at the power flow of a vehicle. So that's the basics of power flow. So what we'll talk about this more online,